Right, so this is the last lecture of the semester, sequencing of separation trains, and now we're going to talk about dynamic programming. And when you talk about programming, it's not to do with coding. Programming is an old term used to describe optimization. And we'll be doing optimization in the first week of next semester when we do CPS 420. And I will just be looking broadly at the types of optimization techniques that you can use. And then I will be giving you an Aspen problem to solve. Aspen has got an optimization routine built in, but you will start to see the techniques as you use that Aspen program. So that is something that I'm banking on. If we're starting our new semester in August, that the lockdown rules will be sufficiently relaxed that we will have access to Aspen, that you'll be able to go into the computer labs and be able to do the assignment. If not, we'll make another plan, and that's okay. I'll just give you an assignment that does use an optimization routine, and that could be on Excel or something like that. Yeah, Jacques-Louis?
So just because we missed a couple of the Aspen tats this semester, I think it might also be a good idea to have some of them next semester to give that learning opportunity as well.
That's great. Yes, I agree with you. That's fine. I think as soon as you can
make them available.
Yeah, look, they're available. In fact, yes, they're available on this semester's the stats themselves that you can go and do on your own. You know, when you do those stats, you very seldom need my help there. So what I should do is to just make them available on CPS 420 as well, or CPJ. I'll make them available on CPJ, so that you can still go through them on your own, and perhaps if you have trouble, to just ask me what you're doing wrong. Screenshot and send it to me on email or something like that. Yes, but I agree. There's some important aspects that we haven't done, and that the one is, of course, distillation and how to do side stream, how to pull off side streams on distillation columns. That's one of the tuts that we've missed. And the other one is how to handle solids. And solids in Aspen is something that I've used a lot of. I've had to, in the South African context, you often have processes that involve solids. And so it is important that you know how to use solids in a simulation program. And Aspen handles them particularly well compared to other simulation programs. So yes, it is something that you guys still need to catch up on. But I'm hoping, and I'm pretty much counting on that we will have access to Aspen by August. Right. So dynamic programming is just an optimization technique. So when we're sequencing separation trains, let's go on to the next slide. You'll remember this slide we've talked about before. Let me get my pointer on. So we have to estimate an annualized cost, and that means that we must take into account capital cost and the running cost. And to get for a single distillation column, to understand what is the capital cost and running cost, we must actually design the column. So in the past, you've been learning how to choose a column pressure, and then you need to estimate number of stages and reflux ratio by the Fenske-Underwood-Gilliland method. And that you use DSTWU in Aspen Plus. Then you select tray spacing, which gives you your column height, compute the tower diameter using a flooding, based on a flooding velocity, fair correlation. And then you estimate the installed cost of the tower. Once you've got the diameter and the height, you can estimate the installed cost of the tower. You size and cost the ancillary equipment, because now you know how many kilowatts is a condenser, what cooling medium you're using, the reboiler, the reflux drum, and you get the total capital investment. So once you've designed it, you know how much it's going to cost you to put up that distillation column. The other thing that you need then is the annual cost of heating and cooling utilities, and that's COS is cost of sales. Cost of sales is to do with how much it costs to run a business. So that's running cost. So now you've got COS. Let's go down to the bottom formula. You've got the cost of sales. That is an annual cost, how much it costs to run your business per year. And then you've got your total capital investment. And then we multiplied that, we divided that total capital investment by 5 in the past. And I was suggesting, because the cost of capital is higher in South Africa, we're going to divide it by 4 to make it equivalent to an annualized cost. Okay. So those of you who have looked at last year's exam will see that I asked a question on dynamic programming, where you will find the optimum sequence when you calculate the annualized cost based on 0.25 over here, or based on 0.2, as you've got in previous slides. And it is possible that you can get different answers for the optimum sequence of columns if you have a different cost of capital. So that R is just giving an idea of how much it costs to borrow that capital to build your plant, total cost of capital, how much you have to pay per year to pay off that total capital. So if you pay that over 4 years, that means R is 0.25. That's how much it'll cost you per annum. That's how much you can use per annum to work out an annualized cost for that distillation column. Right. So let's have a look at mixture A, B, C, D. And you need to work out what the lowest cost sequence is. Now, when you've got A, B, C, D, you can do the first separation that you do, the first distillation column you can do. You could do direct sequence, or you can split it down the middle, or you can take off D first. Those are the 3 possibilities. And when you design those columns, you know, of course, remember, you know how much is the flow rate of A and B and C and D. And you know the relative volatilities. And so you can go and design that column, and you can figure out how much it will cost. So maybe in this case, taking off A first, AB might have the highest relative volatility, and therefore it costs relatively little compared to the other separations. Okay. Once you've done that, let's say that you have an ABC. So you've taken off D, and now you've got an ABC mixture that you need to separate. You can do that in 2 ways. A/BC or AB/C, and you can work out the cost of that distillation column, annualized cost of that distillation column, annualized cost of that distillation column, and you can design those, work out how much they cost per annum. BCD, again, 2 ways of doing it. Annualized cost you can work out. Finally, if you've done, for instance, that separation, AB/C, you've got AB left. There's only one way that you can do an AB separation, but you still need to work out how much that column will cost. And there, AB, not surprisingly, costs less than the other separations, because there we said probably A/B had a very high relative volatility. So it's relatively cheap to do the AB separation. To do a BC separation, 190, CD, but there's only one cost associated. You've got a CD mixture, that's how much it'll cost. If you've got a BC mixture, that's how much it'll cost. But if you've got a mixture of 3 components, there are 2 possible costs. There are 2 possible ways of doing it, and therefore there are 2 possible costs. Okay. So if we do this with conventional lowest cost sequence conventional method, what we're going to do is to say, well, there's our ABCD mixture, and the first separation we can do can be done in those 3 ways that we've just talked about. If you do it this way, A/BCD, then you will have a BCD mixture that you must separate, and that you can do in 2 ways. Let's say you've done it B/CD, you know the cost, then you still got to separate C from D, and now you can add up these 3, the 85, 247, 420, and you get the cost of doing it in this way, which is the direct sequence all the way through. A, then B, then C, and it'll cost 752,000 Rand. Similarly, when you've got a BCD mixture, you could have done BC/D, and then you would still need to separate the B from C, and you'll get 775. All right, so this is a nice, easy problem because we've only got 4 components. When you've got 4 components, there are 5 different ways of doing it. There's the direct sequence. Indirect sequence will be over here at the bottom, and then the in-between methods over here, and then you can separate it right down the middle, and then you'll have 2 binaries. So these are still 3 distillation columns that you need, and you can work out the total cost of all 5 of those sequences. Here's the middle sequence, that's 1 sequence, 3 distillation columns. Here's another sequence of 3 distillation columns, and you get the totals, and you can just see what is the cheapest. Okay, so there you've done your optimization. That is the correct answer. AB/CD, and then A/B and C/D. But that's the conventional way, and this way you've done a lot of calculations, and dynamic programming will just make the number of calculations easier, which doesn't matter so much in a small problem like this, but as soon as you get bigger problems, it is more difficult. Did somebody put up their hand or anything? No. Nothing on chat. Right, so let's go to dynamic programming. With dynamic programming, you actually start working from the so the process flow, the flow of materials is from A, B, C, D, and then you go through a distillation column, and then you go through another distillation column, and then you go through another one. And dynamic programming is a little non-intuitive in that you start working from the back and you go towards the more complex mixture, the mixture with more components. If you've got a binary mixture, there's only one way of doing it, so that is the optimum way because there is only one way of doing it. C from D, it costs 420,000. B from C costs 190,000. There's nothing you can do about it. That is the optimum way of doing it. It's the only way of doing it. But if we go one step further, we look at a a ternary mixture of B, C, and D. So never mind that they're two things here. If you've got a binary mixture of B, C, D, there will be two ways of doing it. And dynamic programming says, yes, you're moving from the back towards the front, towards the start of the process. And then as soon as you can make a decision, are you going to do B/DC or BC/D? You work out what is the optimum. Because once you've worked out this optimum, and here where you can see this is 247 plus 420 to separate a BCD mixture, 667,000. But if you do it by BC/D, it costs more. So you only have to do this calculation once. If you've got a BCD mixture, the best way to do it is this top one that's circled, 667,000. So anytime you come across a BCD mixture, you know in what order to separate them and how much that will cost. That's the optimum. And my normal way of doing it is to put an asterisk at the best way of doing it. To just mark that with an asterisk, that is the best way of doing it. Down here, we don't have a ternary mixture, so this one stays the same. Down here, we've got a ternary mixture of A, B, C, and that can be done in two different ways. If we separate A first, we get 249,000. If we separate C first, we get 212,000. Again, you can put your asterisk over here. This is the optimum way. As soon as you get an A, B, C, this is the optimum way of doing it. First separate C, then A from B. Right. Now we go on to the four-component mixture. And a four-component mixture, you can do it in three ways: A/BCD, AB/CD, ABC/D. Okay, if you do it this way, you've got a BCD mixture, and we've already worked out what is the optimum way to separate a BCD mixture. So now we can add 85,000 to 667,000 and get the optimum way of separating an A/BCD mixture. Yeah, as soon as an A/BCD mixture, we can say is 752,000 Rand. This one is still the same. We'll have our AB/CD mixture. We know how much that costs. And we have to add those two binaries, and we get the same answer. Let's look at this last one. ABC/D. And once you've done that separation, which costs 510,000, you will have an ABC mixture. And we know now how to separate an ABC mixture optimally, and that will cost us 212,000 Rand, and therefore we can work out how much going this route will cost, 722,000 Rand. Now you've got three answers, and this middle one is still the optimum way of doing it. And that's it. That is dynamic programming. Let's just go back to the previous slide. It's a four-component mixture. In the same way, we can have a five-component mixture. And we've now worked out, if we ever have a four-component mixture like this, ABCD, we know that the optimum way of doing it is this way. So if we've got a five-component mixture, one of those ways of doing a five-component mixture is to separate E first, and then we'll have an ABCD mixture, and we know exactly what the optimum way of doing it is, and that's this middle way. If we've got so with a five-component mixture, the other thing we could do would be an A/BCDE, and then we'd have to do the same dynamic programming on a BCDE mixture, and that will give the optimum as well. But again, you always work from the back towards the front in terms of process flow. I just want to mention that these GPS, what you call them, these the things you put in your car that tell you which route is the best way to do it, like Google Maps. They work. They found out the optimum route using dynamic programming, and that means that they don't start. They don't look at all the roads that are leading from where you are. They look at all the roads that are possible to take, all the intersections that are close to where you want to be. And they say, if we move from that intersection back towards your source, where you're coming from, which would be the optimum route to take to get to work? Let's say I'm coming from my home to work. The GPS is going to start at work, at the university, and then it'll start tracking back and saying, if I'm at the intersection of Linwood and University Road, which is the best way to get to work? And then it'll go back and say, if I'm at the intersection of what's that one called? It doesn't matter. Koningen Wilhelmina and whatever. What is the optimum way to get to work? Because then it would have worked that out already. And then it'll work slowly back towards my home, and eventually it'll say this is the optimum. And using dynamic programming cuts down on the number of calculations you need to do. And when you've got so many options, as in a GPS program, and all the different roads you can follow to get to a destination, it really cuts down on the computation time tremendously. Okay, so it's really just showing you the technique, the principles of the technique, so that when you see that in a optimization program, you understand how it's worked. And it's called a branch and bound method. In other words, you've only got discrete possibilities. You don't have a range, a full range of real numbers to optimize. It is once this sequence BCD, you're going to separate by using B/CD as the optimum. That is the answer. It's either that one or that one. It's nothing in between. So that's branch and bound methods, and dynamic programming is one of the branch and bound method. Branch and bound methods. Okay, so all that's left for this lecture is to do the stat. So here is a 5-component mixture, and these are all the possible separations that you might need to do, and the cost, the annualized cost of those 5 separations. So it's exactly the same as in the exam of last year, except that in the exam of last year I have 2 annualized costs, one with a low interest rate and one with a high interest rate. So you've got to do this dynamic programming method twice. So I'm going to switch off the recording and let you try this on a piece of paper, and then in 10 minutes time or so, I'll show you how I went about it, and you can see if that's the right way of doing it. Okay. Let me switch off the recording, and please go ahead, and I will talk to you again at 10 past. Anybody have a question, please just put on your mic and ask. I'll be waiting here until 10 past.